Continuing to continue 2.2, flooding. Flood terms. Flash floods are a quick rise in stream depth. They are caused by intense rainfall of short duration over a relatively small area. They are common in arid environments with steep slopes or little vegetation, following breaks of dams, levees, and ice jams, the upper portion of a drainage basin, and small basins of tributaries of larger streams. Interestingly, most people who die during flash floods are in cars. It only takes about 1.5 feet of moving water, like up to your knees, to wash your car downstream and get caught in a deeper pool or in piled up debris. Fill your car with water and drown whoever is inside. Usually, all these people need to do is wait about a half hour-ish, maybe longer depending on the weather and the geology. But just wait until the water recedes. And for flash floods, that is more like hours, not days. The series of images is of the Rito River in Tucson, Arizona. Normally, this river is just sand. In fact, it can be just sand for several years in a row. This series takes us from shallow water that won't get your socks wet unless you try, to seeing a wave coming down the stream in the next 4 pictures. Then we have peak flow, followed by the water already beginning to slightly recede. At this point, water is rushing by, and I'd have to have some serious motivation to try and cross it. The series of pictures is over less than a half hour. Luckily, people don't even have to think about crossing through this flash flood in their cars, as there is a 4-lane bridge. Downstream floods are a rise in stream depth due to rise in several tributary depths. They cover a wide area, are usually produced by storms of long duration that saturate the soil and produce increased runoff. Can be caused by combination runoff from thousands of tributary basins and are characterized by large rise and fall of discharge at a particular location. The images to the right are an example of a downstream flood of the Ob River in southern Siberia. Floods along the Ob and other rivers in the region claimed the lives of at least 18 people and inundated at least 2,800 homes. Here's a quick comparison between downstream floods and flash floods, or upstream floods. And Clayton is closer to the mountains. Clio is closer to the base level, the ocean. Calhoun Falls is in between, as you can see in the map at the top. Now look at the bottom left graph. Time on the x-axis, discharge on the y-axis. Discharge up in Clayton was relatively small compared to down by Clio. Calhoun Falls is in between. But when you look at the discharge as compared to the size to the watershed, you get a different story. That story is told in the graph on the bottom right. Time on the x-axis, discharge normalized or divided by the area of the watershed is on the y-axis. So basically, it is a measure of how much water is in the stream per square kilometer of the watershed. Clayton has the smallest watershed at 526 kilometers squared. Not surprising, it is the smallest watershed as it is the closest to the headwaters, i.e. doesn't have as many tributaries. It doesn't collect water from quite as large an area as compared to further downstream. In contrast, Clio has the largest watershed at 25,512 kilometers squared. It has way more tributaries, including all the tributaries of the Chattooga River in Clayton, as well as the Savannah River in Calhoun Falls, plus all the tributaries that come into the Savannah River downstream from Calhoun Falls. And if you look at the not very detailed map, I can count 6 other rivers that enter the Savannah River between Calhoun Falls and Clio. So no surprise, Clio has a much bigger watershed. Well, when you divide the discharge by the square kilometers of the watershed, you get a better idea of the magnitude of the flooding that occurred in these different towns. For the watershed size, Clayton got it more than Clio, even though Clio had much bigger, higher overall discharge. Also, you can see the flood had a shorter duration in Clayton than in Clio, typical for upstream floods. 4.5 days versus 14 days. It took less time for the rain to travel into and through the Chattooga River because it was closer to the headwaters. And the tributaries into the Chattooga River were not only shorter, but had less variation in length, bringing much of the water at about the same time. Hence the spike on the graphs. Further downstream in Clio, the flood is much longer because it is farther from where the rain happened in its many tributaries. So longer travel time, with much variation in travel length to get into the Savannah River at Clio. That's why the flood lasted so much longer. It had a more gentle rise and fall in floodwaters and had a much higher discharge in Clio as compared to Clayton. Now, I said nothing about the effect of the flood. That is a whole different story, really dependent on city planners and residents. 6.3 Geographic regions at risk for flooding. Any place that receives precipitation has the potential to flood, which is just about everywhere. Floods are the highest cause of disaster in the United States in the 20th century. All areas of the United States and Canada are vulnerable to floods, even us here in the Boise, Meridian, Nampa area. Can you believe it? We are at risk. 6.4 Effects of flooding and linkages between floods and other hazards. Primary effects of flooding include injury and loss of life, damage caused by currents, debris, and sediment to farms, homes, buildings, railroads, bridges, roads, erosion of sediment leading to loss of soil and vegetation, and deposition of sediment leading to burial of topsoil and loss of vegetation. So both erosion and deposition of sediment can be annoying, though sometimes the deposition of sediment can be useful. Think of the Nile. Secondary effects of flooding include pollution of rivers, hunger and disease, homelessness, and loss of services such as fishing, recreation, and transportation. And so flooding can clean and clear rivers, but also pollute them. How? Think of all those hydrocarbons on cars, oil change places, gas stations getting washed into our river. Think of flooded wastewater treatment centers and sewers. Gross. Factors affecting flood damage include land use on floodplain, depth and velocity of floodwaters, rate of rise and duration of flooding, season, quantity and type of sediment deposited, and effectiveness in forecasting, warning, and evacuation. Land use is obvious, right? Should we build on a floodplain? If we do build on floodplains, what should be built? I vote for parks, but some people vote for malls and neighborhoods. Depth and velocity of floodwaters. Again, obvious, right? Faster and deeper water will cause more damage. Also, more damage will occur if the rise is quick and the flooding lasts long. Season might be less obvious. What might be damaged in a spring flood versus a fall flood? Or think before crops are planted versus after crops are planted. Before harvest or after. Quantity and type of sediment deposited is another obvious one, hopefully. Lots of sediment deposited in building is harder and longer to clean out than less sediment. And farmers might like organic rich sediment placed on their fields, but cursed sand and cobble deposits. And if effectiveness of forecasting, warning, and evacuation is poor, lives may be lost that could have been saved, making the flood damage much more severe. Linkages with other natural hazards. Flooding can result from hurricanes, earthquakes, i.e. tsunamis, landslides, i.e. blocking streams, and others. Can you think of any? Sky's the limit. Just be sure you can justify your answer. Image is of flooding in Sumatra, Indonesia in 2004 after the earthquake and subsequent tsunami. Flooding can cause fires as they produce shorts in electrical circuits and erode and break natural gas mains, coastal erosion, and others. Again, can you think of any? Sky's the limit. Just be sure you can justify your answer. You can always email me your thoughts. If I like them, I'll share them with the class. The images are top results of a fire in floodwaters, and bottom, floodwaters causing coastal erosion as they flow to the ocean. 6.5. Natural service functions of floods. They include fertile lands if sediment deposited is of high quality, i.e. lots of yummy organic matter full of nutrients. Aquatic ecosystems can be maintained and developed as the flood flushes out some debris, making some deeper, cool pools favorable for some fish, and leaves other debris and nutrients, especially favorable for hatchling habitat. Groundwater recharge is favored by water hanging out over a large area for a while, increased percolation into the ground. And sediment supply is critical, especially for low-lying areas. That's what the pictures are showing. The top picture is the Mississippi Delta at New Orleans in 2010. The Mississippi River has been highly regulated and hasn't been allowed to change its course much, or even flood into low-lying areas. The Mississippi River definitely carries a bunch of sediment. That formed the delta under New Orleans in the first place, but now is making a new one out in the Gulf. If that trend continues, by 2100, a lot of the old delta, which is sediment starved, will decay, sink, and erode below sea level, as depicted in the bottom image, which would be unfortunate for many people. Sediment supply is useful. Human interaction with flooding. To understand human interaction with flooding, we need to understand the concept of dynamic equilibrium. This equilibrium is a balance between gradient, cross-sectional shape, and flow velocity for discharge and sediment load. We'll discuss. But first, know that rivers generally maintain a dynamic equilibrium, meaning that they change fairly quickly in response to changes. Change in the amount of water or sediment received by a stream changes gradient or cross-sectional shape, which changes the velocity. All these changes are related, so you can start by changing something else. Say the cross-sectional shape, like if you channelized the stream, would change the velocity of the water, which changes the sediment load, etc. I'm going to walk you through two specific examples. Try to think like a river and understand the process, rather than just memorize things.